So before I start this, just some details about a contest that's happening next week. So next Tuesday, we're hosting a contest with CSE Soc and IMC, the IMC programming contest. That is next Tuesday, the 23rd, starting at 5 till 7 p.m., I think. More details on the Facebook event. So definitely check that out. There's, I think, quite a lot of prizes. I think it's $2,000 in prizes. Correct me if I'm wrong. So definitely worth doing that. Teams of 3. It's a 2-hour contest. So take a look at that event after this workshop. But otherwise, let's get started.
Also, just quickly, it's like a very beginner-friendly contest. So if you're here and you're free at that time, I don't see any reason not to enter.
Yeah, so there's 2 divisions. There's one division for people who are new, one division for people who are more experienced. So yeah, beginner friendly. Also for those who are more experienced, wide range of people. So today's workshop, we're going to cover quickly a refresher intro of stacks. That should be not take too long. Then we have 3 problems of increasing difficulty going through usage of stacks. So if you find the beginning part a bit easy, then the end part will be more difficult, or yeah, so get more difficult as we go along. So let's get straight into it. What is a stack? So a stack is a data structure, supports 3 operations. So you've got like a stack, add an item to top of the stack. So you've got your stack here, we can add an item, often a number. So let's add, say, 3 to our stack. And then we can add 2 to our stack. We also support remove the top item from the stack. So we can go, well, we don't want 2 anymore. Let's remove that from our stack. Just erase that, I guess. And our third operation is view the top item of the stack. So we can say, what's the top so far? Top is 3. Can push 1 on. Top is now 1. Push 2. Top is now 2. Pop 2. The top is now 1. Put 4 on. Top is now 4, etc. And pop that. So it simulates kind of a stack in real life or a pile of objects in real life. And while it might not seem immediately powerful, as we'll see throughout this session, it is actually quite powerful and there's a lot of things you can do with it. So each operation can be supported in constant time. So one way to do this is keep an array. And so you put the bottom of the stack here. As you add an item, you like put like 1, 2, then the top of the stack, you just remove this, etc. So that will have constant time per operation because you're just accessing an array. Again, if you're not familiar with time complexity, if you're here, let me know. Otherwise, check out last week's session where he went over some intro to time complexity. Also, again, we're not going to cover linked lists now. They're not required knowledge, but you can use a linked list as well to implement a stack. So stacks in C++. So C++ supports hash include stack. So like your hash includes in C, this includes something which lets you use a stack. So very quickly how you use it. Declare a stack like this. This is a stack of integers. You can push stuff onto the stack. So push 3, it adds 3 to our stack. Print the top of the stack, it prints 3. Print the size of the stack, it prints 1. Then we can push 1 onto our stack. Push 2 onto our stack. Top of the stack now prints 2. Size of the stack is going to be 3. We pop the top thing off the stack. The top of the stack is now 1. The size of the stack is now 2, etc. We can push 4 on. Again, it kind of keeps going. So yeah, it helps us a lot because rather than having to say use an array to implement a stack or using a linked list to implement a stack, we can use this default data structure. Now behind the scenes, this will be using, I think a linked list is what it uses by default, but we don't care about that. All we care about is we have this kind of interface we can use to access stack, which is quite nice. So that's all for the stack refresher. Now onto some problems. So in the first problem here, it's bracket matching, something which often you use stacks for. So in this problem, you're given a sequence consisting of open and closed brackets of various forms. So you could have like this. So a sequence could be like open, open, 2 of these, 2 of these, and like some curly braces. And a bracket sequence is valid if we've got a recursive definition here. So saying the empty string is a valid bracket sequence. So just like a blank string is valid. Otherwise, if you have a valid bracket sequence, you can put brackets around it or combine two valid bracket sequences. But don't worry too much about that formal definition. All it means is that all the brackets match nicely. So in this example down here, these two match, these two match, these two match, and these two match. So our conditions are each bracket matches with another bracket of the same type. So for example, this here is not valid because they're different types of brackets, but this is valid. This is also not valid because not everything matches. These two match, but this matches with nothing. Again, this is not valid either because these two match, but this is unmatched. But this is valid, and as is, for example, a sequence like, I don't know, open square, close square, that open curly brackets, some round brackets, some square brackets in round brackets, etc. This is valid because, again, we can say, well, these two match, 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 match. So we just have to determine, given a bracket sequence up to 100,000 characters, is it valid? And some sample input here. The answer is yes. Again, we can just go match, match, match. That doesn't match, sorry. Match, 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 match. Match is there, but it's on the fly. Match, then these match, and these match. So the answer is yes. But then this sequence here, the answer is no, because different types of brackets, so that doesn't match. So I guess any suggestions on how you might go about this? I'll give you, I don't know, 10 or 20 seconds to make a suggestion. Otherwise, I'll just go forward and explain a solution. All right, so I guess first up, as I was drawing it, you notice that to see if a bracket sequence was valid, I just matched them up. So if a bracket sequence is valid, we should be able to find the match of each bracket. By that, I just mean for each opening bracket, we should find which closing bracket it matches up with, because if it's valid, this has to be possible. And so an informal observation is we want to assign each closing bracket to the closest available opening bracket. So that's just what I was doing by hand. If we have like an open bracket and a closing bracket, we assign these. So that's how the bracket matching works. So closest available informally means like that. We can formalize this by processing the string one bracket at a time and considering what we do with each bracket as we get it. So let's write out a sequence at the top here. We'll go squiggly, squiggly, close like this. Okay. An opening, this doesn't work. Let's move this, draw it over here. Open, open, square, squiggly brackets, close like this, for example. And wait a second. And then open, open, close. That should be a valid matching sequence. So an opening bracket will match with some closing bracket in the future. A closing bracket will match with the nearest unmatched opening bracket. And we'll do this with a stack. So we push the opening brackets onto a stack. So if we start off here, we're going to have our stack down here. So we've got our stack down here. And so we get to this first one here, and we push the opening bracket onto the stack. We push the second opening bracket onto our stack going sideways. We push this third opening bracket onto our stack. We then get to a closing bracket. We get to a closing square bracket like this, and we go, okay, the closing square bracket should match with the most recent opening bracket, which is the top of the stack. So we look at the top of the stack and we go, oh, the top of the stack is a square bracket, which means these two pair, we pop this off the stack. We then go, okay, opening curly bracket, push it onto the stack, closing curly bracket, look at top of the stack, oh, it's an opening curly bracket, pop that off the stack, these ones match. We then get to a closing round bracket, we see, oh, top of the stack, one of these ones, so pop it off. We then here, opening bracket, push it on, closing bracket, pop off, closing bracket, pop this off. We get to the end, the stack is empty. So this is the yes result. Under what conditions might there be a no result? So what might be the case of our stack that will lead our algorithm to say no? This is not a valid matching. Any suggestions? Well, there are a few of them. So first of all, we match different types of brackets together. Remember, in the question, we had to match the same types of brackets. So if you get this as a sequence, for example, we'll push this opening bracket onto the stack. We'll get to a closing bracket. We look at the stack. We see, oh, the top of the stack is a round opening bracket, but I'm a square closing bracket. We don't match. Therefore, print no. We're done. Second condition, there's no unmatched opening bracket for a closing bracket. In other words, the stack is empty. So if we have like this, for example, we push this onto the stack, we then pop it off the stack, we get here, we're a closing bracket, but the stack is empty. That means there's no brackets for us to match with, and so the answer is no. Finally, there are unmatched opening brackets at the end. So the input instead is like this. We see that, oh, at the end, our stack will look like this. Because we pushed 3 on, we popped 1 off. Our final stack was non-empty, which means there were some unmatched opening brackets, which means the answer is no. Our matching is not valid. So we have a solution now. Again, let me know if you have any questions about that. But otherwise, the time complexity. Well, we do constant work, order 1 work for each of the end brackets. Constant work, why? Because we either push something onto the stack or pop something off the stack. They're both constant time operations. So constant time over n brackets, so order n. Remember, the bounds originally, if I go back, was n up to 100,000. So doing order n work is perfect for this. So here's some code. So I'll quickly go over it. It's on 2 pages. So here we do hash includes. Here we just make a no function, which says it prints no and ends our program. It just makes it easier for our code to run, not too important. Here we just scan in the input. We then go for each thing. If it's an opening bracket, we check that here. Just push it onto our stack, as we did by hand before. Otherwise, if it's a closing bracket, if our stack is empty, we print no and end the program. Why? Because there's no opening brackets for us to match with. Otherwise, if we're a round bracket, but the top of the stack is not a round bracket, so it's square or curly, again, no. Similarly, if the top of the stack is square and we're not square, we print no, etc., etc. We then pop the top of the stack because we matched with them. If the stack's empty, no, otherwise print yes because we didn't print no. Okay, on to our second problem, sculpture 2. So in this problem, it's a bit harder than the last one, but still not too bad. In this problem, we have n Lego blocks, and we're going to create a structure on a line. I'll explain what that means. So the ith block is wi by hi tool. So we have wi hi. So it's a rectangle. And after ti seconds, so this block will magically fall from the sky with its right end ti centimeters along the line, measured from the right. So some diagrams. Also, I'll do diagrams in a second, but the question is, what is the highest point on the sculpture overall? And also, if a block lands on another, it'll stick to it. So for example, we have one block that's like this, so 1 by 2, and lands after 1 second. We have another block that's going to be 2 by 1, or 2 by 2 actually, it lands after 3 seconds. And finally, a block that's going to be 1 by 4 that lands after 4 seconds. So we have our thing here. After 1 second, so this block lands with its right endpoint at 1. So remember, it's too wide, so it goes like this. After 3 seconds, this block falls again with its right endpoint at 3. So it's like this. Again, too wide, so it goes all the way up to 5. Finally, after 4 seconds, this block lands. And if a block lands on top of another one, it sticks to it. So it sticks like this. We see the overall height of our sculpture is 3 because that's the maximum height. More diagrams on this slide that are a bit nicer than my handwriting. So the first block, for example, lands after 1 second. So we have 0 here, 1 here, 2, 3, 4. So it lands after 1 second. So its right side is at 1. And it has width 3, height 2. Then a second block with time is 2. So again, we have 2 here. With width 2, height 1 lands. It sticks to the top like that. Finally, a third block with width 2, height 1 at time equals 3 lands. So its right endpoint is at time equals 3. Like this. And then finally, a fourth one goes in there at time equals 5. So this has got 1, 2, 3, 4, 5. Its right endpoint is on 5. But it just misses this one, so it doesn't land on top of it. It goes next to it. And the question is, what's the maximum height of the sculpture? Well, in this case, it's 4. It's 4 because 1, 2, 3, 4. So on to the next slide then. So the height of the sculpture is 4. The bounds on this problem, they're up to 100,000 blocks. Each block is up to 1 million by 1 million in size. Oh no, sorry, 1 million wide, but its height is up to 1,000. So it could be 1 million here, but only 1,000 tall. And it could land up to after 1 million seconds afterwards. And remember, if it lands after 1 million seconds, it lands at position 1 million on the thing. Finally, the blocks are given sorted by time. So the ith block lands before the ith plus 1, 1. That was a bit hard to say, but the blocks arrive, or you're given the blocks in the input in increasing order of time, and also all times are unique. So 2 blocks won't fall at the same time. You don't need to worry about that and what happens in that case. So that's the question. The source of the question is, or subtask, sorry, all values up to 1,000. This one here is all blocks the same dimensions. We're not going to look at this subtask today, so don't worry about it. And finally, the full solution. And the source is from the AIO. So do people understand what the question is asking? Or are there any queries about what's being asked? It's the yes in the chat if you understand what's going on. Or a no in the chat if you don't understand what's going on. I'll take silence as a yes. So we'll go over a solution now. Feel free to say anything in the chat or unmute your mic. Otherwise, I'll just go straight into it. So first of all, observe that each block will sit on top of at most one other block. This is actually quite a non-trivial observation. And it comes from, let's just draw out like what the process looks like. So what if remember one block sitting on more than one? So what if we had like this? We have one block here, another block here, and then one block that sits on top of both of them like this. But this is not possible. Why is it not possible? Because of the ordering in which blocks arrive. Remember, blocks land in the order which they're positioned, because the position they arrive is equal to the coordinate, their rightmost coordinate. So the order in which these 3 blocks must have landed is 1, 2, 3, because the order of the blocks landing is defined by their right endpoint. And if they arrive in order 1, 2, 3, then this block wouldn't be here. It would be on top here. So this construction is impossible. And similar constructions are still impossible. So you couldn't have, like an even worse example would be like this. Oh, sorry, like this. Similar reason that's impossible, because the ordering would now be 1, 2, 3. Oh, so like we would be having 1, 2, 3. And so the order they would have been landed would have been instead like this. This one would have landed first, then this on top, then this on top. And so every block will sit on top of exactly one other block. I think my drawings might be a bit lagged. Am I having internet issues, or can people hear me fine? Because I think I'm getting some lag on my drawings. Don't know if
we can hear you fine right now, but your voice was lagging a bit before.
Yeah, that's uni-wide for you. Okay, so this is an important observation. So another way of saying this is when the ith block is placed, there's a single stack of blocks which it falls on top of, because each block is on top of exactly one other block or on top of nothing. So the example in the sample input looks something like this. 1, 2, 3, 4. By single stack, I kind of mean, well, we have this structure and then this on its own. It can look something a bit different. It can look like 1, 2, like 3, and then like 1 here, and then 1 here and 1 here. For each block, there's a single stack. So like for this block here, its stack is like this. For this block here, its stack is like this. So each block still has a single stack which lies directly underneath it, that's supporting it. Because each block has one block below it, that one has one below it, etc. And this is quite a nice structure. We can play with it. And it is interesting that I use the word stack here, because does this stack have the properties of a stack? Well, the answer is yes, it does. When a new block is added, it's added to the top of the stack. So when we put a new block on, we put it on top of another block. And a block only goes because the stack is defined as the top of the stack is the block below us. We, by definition, a new block gets put on top of the old top of the stack. And so there's a bit of maths going on here, but if the TI, that is the right location of the new block, is larger than the right location of the old block plus the width of the old block, so we have the old block here, we have TJ, and we have TJ plus the width, WJ, because remember the width here is WJ. If the location of the new block is bigger than this, so like for example, its TI is larger, it goes like here, then we have that the new block does not land on the old top of the stack because it lands past the top of the stack. So we should pop the top of the stack because our blocks arrive in sorted order of location, no other block will ever land on top of this block here. So we can pop it from the stack. Perhaps a nice example to see this is one where we have like this block here, this block here, this here, then this here. So our stack looks like we process the blocks in sorted order and we go, okay, push this one onto the stack, push this onto the stack, push this onto the stack. We then get to this last block here. We go, okay, what's the old top of the stack? That's this block here. We see that, oh, but we're past that block. So we pop that off the stack and then push ourselves on top of this. And so at any point in time, we can maintain a stack that simulates the current tower that this block is on top of. And another thing, a block in the middle of the stack will remain on the stack for at least as long as the block on top of it does. This is because if we have like this block here and this block here, because this one is on top of this one, the lower block will keep supporting any upper blocks which lie on top of this middle one here. That's what that last dot point means. And because of that, this process motivates a stack solution. So we process the blocks in order and maintain a stack. We also keep track of the current height of all the blocks in the stack behind and the highest stack we've seen so far. So I'll go over an example to demonstrate what this means. When we reach a new block, we pop the top of the stack while this condition here. Remember, we pop the top of the stack while the top of the stack is like not relevant anymore. That is, the new block won't land on the old block. We pop it off the stack. We then push our new block onto the stack. We update the high stack we've seen so far if our current stack exceeds that. So an example, let's say we have, I'll draw out the final input first. It looks like block, 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 and then block here. What do we do? We'll keep our stack, I'll number them. 1, 2, 3, 4, 5, 6. We process number 1, our stack, we push 1 onto the stack. And let's say the heights of these are all going to be height 1, height 1, height 1, height 1, height 1, height 3, let's say. So we push 1 onto the stack. We then push 2 onto the stack. Then we push 3 onto the stack. And we push 4 onto the stack. At each point in time, we keep track of the height of the stack. That's not the number of elements in the stack. That's a sum of the heights of all the elements in the stack. So which in this case corresponds to the number of elements in it, but it won't always. So after we push 1 onto the stack, for example, the height of the stack is 1. After 2, the height of the stack is 2. After 3, the height of the stack is 3. And after 4, the height of the stack is 4. And so we record somewhere, the biggest stack height we've seen so far is 4. We get to 5 here. We see, oh, 5 won't land on top of 4, so pop 4 off the stack. 5 won't land on top of 3, so pop 3 off the stack. But 5 will land on 2, so we push 5 on top of 2. The new stack height is 3. We see, oh, 3 doesn't beat our biggest maximum, so the highest height is still 4. We then get to 6. We pop 5 off the stack because 6 won't land on 5. We pop 2 and 1 off the stack. We then push 6 onto the stack. We see that what's the height of the stack? The height of the stack is 3. 3 is less than 4 still. Okay. The biggest one we've seen so far is still 4. We get to the end. What's our answer? Well, it's the biggest stack we saw, which is 4. Let me know if you're confused about any part of the solution. Otherwise, I'll just move on to the time complexity. What is it? Anyone want to chime up and say what the time complexity of this solution is? I'll give you 10 seconds before I go to the next slide. No one? Okay. So some reasoning. We process each block once, and for each block, we pop some number of things off the stack and then push one thing onto the stack each time. However, each block is only popped off the stack once throughout the entire solution. So even though in our last example, when we got to block number 5, block number 6, we popped about 4 things off the stack. But because on average, we only pop one thing off the stack, because over the entire solution, we pop everything off the stack once, we do n pushes onto the stack throughout the entire solution. We do n pops from the stack across the entire solution. So the overall complexity is order n. So linear time, which is, you can't get any better for this problem because the input size is linear. So this is just linear. So we have a solution that's fast enough. Remember again, n was up to 100,000. So order n will pass and be fast enough. Okay, that's this problem. Again, let me know if you have any questions. Otherwise, I'll move on to the code. So very briefly, This is just some setup here, declaring some arrays, scanning the input. So again, initially we pop stuff off the stack when this condition here is true. That's that condition ti is greater than tj plus wj that I mentioned before. We also check, is the stack not empty? Because we don't want to pop from an empty stack. That'll actually crash our program. So we'll check if the stack is not empty. So if there is something on the stack and our current element will not land on top of the old top of the stack, we pop the stack and we also decrement. We keep checking the current height of the stack. We just decrement that. We then, after breaking out of this while loop, we then add our current height. So add our height to the height of the current stack. We then check, is our current height the best we've seen so far? And then push ourselves onto the stack and print out the answer. Again, the nice thing about this problem, although the solution was a bit involved, the code is very simple. The actual logic of the code is like 6 lines or something. The rest of it is just input and output and declaring variables. So the actual code is, yeah, about 6 or 7 lines. Not very much. That's that problem. On to our third and final problem. It's a bit more difficult, but a nice example of how powerful stacks can be. So in this problem, you're given a histogram. A histogram is a shape consisting of a number of bars of equal width, but various height. So this is the histogram here. So all the bars have like a common base here, but they all have different heights. And the question is, what's the area of the largest rectangle contained within the histogram? So I guess some examples. There is a 2 by 2 rectangle here. The heights are like 1, 2, 2, 5. There's a 2 by 2 rectangle here. So area 4. We also have under here an area 1 by 8. So area 8 rectangle. Here we have another area 8 rectangle, 2 by 4. Here we have like an area 5 rectangle. But the best we can do, here we have an area 9 rectangle, 3 by 3. And that is, perhaps you can see it from this diagram, perhaps you can't, but just believe me when I say this is the biggest axis-aligned rectangle that lies under this histogram. So the answer to this problem, what's the largest area under this given histogram, is 9. Any questions about that? If not, input-output formats. So not that important, but we're given n, the number of bars, and then the heights of the bars in order. And you just output the area of the largest histogram. So for example, n up to 100,000, heights up to 1,000,000, that's the bounds. So up to 100,000 bars, so quite a big histogram, and quite tall, up to 1,000,000 tall. But some subtasks, so n up to 100, so smaller histogram, slightly larger histogram, and then a massive histogram. So we'll go through subtask by subtask to build up to the full solution, because this is a bit harder. So the first solution will be quite simple, a bit harder, and then building up from there. So quickly, sample input. This sample is just our diagram. So we said height 2, then height 3, then height 1. This is like 2, 3, 1. That's exactly 2, 3, 1, 5, 3, 4, 2, 1. Is exactly this thing here. The output's 9. That's the largest rectangle under the histogram. Okay. If there are no questions about the problem, we'll go straight into finding a solution. So subtask 1, n up to 100. My first note is this bound allows an n cubed solution. So n cubed gives us 1,000,000. 100 cubed is 1,000,000. Order n to the power of 4 might pass. It's about 100 million. That's pushing it. But we can definitely find an n cubed solution with these bounds. So any suggestions on what that solution might be? I'll give you about 30 seconds to give any ideas, observations, anything. If not, I'll move on to explaining the solution. Give you another 20 seconds or so. Chat's very silent. Okay, so I'll just go through some details. So an observation we can make, the optimal rectangle will always have an edge along the bottom of the histogram. So go back to our diagram. The optimal rectangle won't be like this, for example, because we might as well extend it downwards to here. Because remember, all our histogram bars have their base along this common line here. So we can always extend our rectangle downwards. So the optimal rectangle, the rectangle with the largest area, will always have its base along here. Additionally, it'll cover some range. So here it covers like the 4th bar to the 7th bar, and it'll extend as far upwards as it can. So it'll extend up all the way until the smallest of the bars it covers. Because again, if we didn't go the whole way up, or we can make our area bigger by going the whole way up. So we might as well do that. So observations, if we know the range we cover, then we know the rectangle, because we'll go from the bottom to as high as we can go. So that can inspire some solutions. So back to here. We'll just consider all n squared ranges that could form the base of our rectangle. Why they're n squared? Well, we've got our histogram here. We have n possible starting locations. So we can start at we can start here or here or here or here or here. So there's n possible left bounds for our range. There's n possible right bounds for our range. So order n squared, actually n choose 2, but order n squared ranges. So we consider each range. And for each range, we just find the height of the minimum bar in that range. So find the smallest bar. This, if done naively, takes order n time. Why? For each range, we just iterate over every bar in that range. So we go, okay, check the first bar, check the second bar, check the third bar. What's the smallest? Our area is width times height of smallest. Do this for every possible range. We'll get the solution, because the solution will be one of those ranges. So order n squared complexity. Very quickly, my code for that, it does exactly what I said it would do. So it goes input for each range. So for each range ij, we find the height of the smallest bar in this range. That shouldn't say bar, it's just the height of the smallest bar in this range. We do this by a simple for loop. The function min returns the smallest of 2 values, so we find the minimum one, and then we update our answer with the area, which is the width. J take I times 1 is the width of this range, times min. And then we output the answer. So order n cubed, because n cubed. Okay, n cubed is a bit slow, it gets one subtask, but we want faster than n cubed. So how can we go faster? Well, with this bounce, we can allow an n squared solution. And there's quite a nice optimization, quite a simple optimization from the last solution to this solution. Anyone want to say what it is? Otherwise, I'll just go straight into it. I'll give you 10 seconds or so. All right, let's get straight into it. So in our last solution, we considered each of the order n squared ranges. So we considered order n squared ranges. And then for each one, we had a third for loop to check, well, what is the height of the smallest bar in that range? And that was that makes it from n squared to n cubed. So let's try and optimize this part of it out. So how might we do that? Well, observe that the minimum what we're saying is minimum of I to j. So the min of like I through to j equal to the minimum of I through to j minus 1, and then just j. So j there. So if we know the minimum value in this range, for this range, rather than recomputing the entire thing, we'll just go, what's the smallest in this range? And compare it with the single value that's here. And that will in fact improve our solution by quite a lot. So more formally, consider each starting of the range. For each I, we consider each j, so we increase our range bit by bit. And as we increase our range, we keep track of the smallest bar we've seen. So in this range, it's just I. Here we check, is the new value, when we increase our range by 1, is the new value smaller, yes or no? And we keep extending our range. And as we extend it, we keep track of the smallest bar. This removes that inner for loop because we have that smallest bar in there. And so we have 2 nets of for loops instead of 3. And there's a constant amount of work within each loop. So our complexity is now n squared. So a small optimization made our code a whole lot faster. So again, for completeness, here's that code. So our order n squared solution, it's very similar to before. I copied the same code. The main difference is for each starting position, we keep track of the minimum so far. Initially, the minimum is just the first one. At each point, we update our minimum to say it's the smallest of our minimum so far and the current bar. And then we just update our area, the same as the last code. So in fact, our code is even shorter. We cut out one for loop. It's much faster, n squared. So it can pass n up to 1,000, or even n up to 5,000 could probably pass. But that's about it. We're still not at a full solution, but we've improved it. So let me know if this doesn't make any sense, or there will be splitting. We won't be building off this solution, because one thing to note, we're able to optimize our n cubed solution to an n squared solution because of the unnecessary inner loop. We could optimize that out. But in our n squared solution, it's quite hard to optimize. And like an informal justification for that is that in our n squared solution, we consider n squared ranges individually. And for each of those n squared ranges, we find its area, and then we compare its area to our maximum so far. Now, we can't improve the solution beyond order n squared unless we change our approach, because we can't consider each of the n ranges individually, no matter how, and each of the n squared ranges individually, no matter how fast we do it, it's still order n squared if we consider each range individually. That is, each base range on the base individually. So we have to not just optimize our existing solution, we have to adopt a new solution, try a new approach. This is common, not just in stack problems, not just in this problem, but in lots of problems. Sometimes you get a solution that's just hard to optimize, and you need to adopt a new strategy. And often when the fundamental kind of basis of the solution is too slow, that's when you need a new strategy. It can use ideas from the old one, but it needs to like fundamentally change. It's not just a small optimization. So let's try something new. So before, remember, we fixed the range on the base. Let's try something new. Remember, for each range, it's the smallest bar in that range that determines the height. So for this rectangle here, the optimal one, it was this bar here that determines its range. So let's predetermine the smallest bar in the range. So let's say, okay, well, what happens if this bar here, what happens like if this bar here is the smallest in the range? We're going to say, okay, this bar is the smallest in the range. What's the biggest rectangle we can get? Well, it's this rectangle, right? We can go all the way to the left and all the way to the right. Okay, what about this one? What happens if this rectangle, this bar, sorry, is the smallest height? Well, in fact, we can't go left or we can't go right because this bar is smaller and this bar is smaller. So if this one is the smallest in our range, then it's going to form the rectangle on its own. So area 4. What about if this bar here is the smallest in the range? Well, we can extend leftwards to cover this one, but we can't cover this one because it's lower. And we can extend rightwards to cover this one, but we can't cover this one because it's too small. So we get this range, the optimal range. And notice that the optimal solution can always be described in this way because every range has the smallest rectangle, smallest bar, sorry. We get the smallest bar and we just extend leftwards as far as we can go. We then go as far right as we can go and take that area. And notice there are order n, or there are exactly n bars, which could be the smallest possible bar. So if we try each one individually, we're trying order n things. So for each eye, we assume that it's the smallest bar in the rectangle. So go one by one and we go, okay, what if this one here is the smallest one? What if this one here is the smallest one, etc. And at some point, we'll get the solution because at some point, we'll try the bar that is the smallest one. We want to find the first bar to the left of it that's smaller than it. Why is that? Because again, when this bar is the smallest one, we can extend left until we hit a bar that's smaller than us, or we hit the end. In this case, we get this one here, which is smaller. Same thing for the right. We can extend rightwards for as long as we want until we hit a bar that's smaller than us. So if this bar is the smallest in our range, we're going to find the first one to the left that's smaller than us, which we call the left limiting bar. That's just terminology that I made up. So don't go using it elsewhere. And on the right, we find the smallest bar that's smaller than us. Call that the right limiting bar. If we know the left limiting bar and the right limiting bar, then we can find the area. Why? Because the left and right defines the width of this. So like R minus L, take 1, I think, gives us the width. The height, well, we've already determined the height because we said this one's the smallest in the range. That's the height. And so we have our area. So for each bar, we assume it's the smallest. We want to find its left limiting bar, its right limiting bar, and then we know its area. We do this for every bar, and the biggest one will have our answer. That's what I just said. Now, how do we find the left limiting bar and the right limiting bar? Well, naively, we can do an order n time. How to do that? Well, back to our example. We start here and we go, is the bar next to me my left limiting bar? No. Try again. Is the bar next to that the left limiting bar? Yes, it is. In the worst case, we loop over n things. So it's order n time. We just keep going back until we find the left limiting bar. This one here, for example, this one here, we'd have to go like 1, 2, 3, 4 to go back 4 things until we get the left limiting bar. So it'll take us a little while. So that's why it's order n time. And we do exactly the same thing for the right. In fact, because the process of finding the left and right limiting bars is the same thing just in reverse, from now on, I'm just going to assume we're finding the left one. Because whatever process we find the left one with, we can run exactly the same process on the right. So just assume we're finding just the left limiting bar because the right is the same process. So we can find the left limiting bar in order n time. That's another order n squared solution. That's not good. We don't want that. However, this is more promising than our last solution because of the fact that we can potentially optimize this because we have like order n things to consider and then order n work. So if we can optimize this line here, then we have a faster solution. So let's try and optimize this. So we're going to use a technique called a sorted stack to do this. So to solve the problem of for each bar, find its left limiting bar. So how do we do that? Well, let's make some observations. Imagine we have 2 bars here. So in this case, we have the red one here, red and green here. So red, green. And consider some bar in the future. Like here. My claim is, no matter what bar goes here, this red one will never be the left limiting bar. Why is that? That's because the green one here is further to the right and smaller than it, which means that, like, 3 cases. Case 1, the new bar is smaller than both, in which case neither is the left limiting bar. Case 2, the first bar is bigger than this one, but smaller than this one. The green one is left limiting now. Finally, this first one's even bigger. The green one is still left limiting. In no case is the red one left limiting. So that's just like out of consideration now because we've got a smaller one to the right of it. However, in this case, both of them could be left limiting. Case 1, neither are left limiting. Case 2, the purple one here, is left limiting. Case 3, the blue one is left limiting. So in this case where they're in like sorted order, both of them could potentially be left limiting depending on what the next bar is. But in this first case, we can safely ignore the red one. So that's what we're going to do. So we're going to go from left to right. We're going to process from left to right. At each point in time, we're going to keep track of the set of bars that could, at any point in time, be a left limiting bar in the future. And let's see what that looks like. So first of all, we consider this bar here. Now, obviously there are no possible left limiting bars because there's no bars before it. So the first bar has no left limit because there's nothing to the left of it. Now we mark this bar as a possible left limiting bar. So I mark it green to say, okay, this one could be left limiting in the future. We're now considering this bar and we see, oh, in fact, this green one is my left limiting bar. So we've found a left limit. I'll just draw that along the bottom. We have found the left limit here. Now we go to this third bar here. We mark this new bar here, bar 2, as being green because it could possibly be a left limit in the future. However, notice that this bar here is smaller than this one here, which means 2 things. First of all, obviously bar 2 here, so bar 1, bar 2. Bar 2 is not the left limit of bar 3 because bar 3 is smaller than it. But from before, bar 2 is our red bar from before. Bar 2 in the future will never be a left limiting bar because bar 3 is always going to be smaller than it. So we can mark bar 2 as not green anymore because it will never be a left limiting bar in the future. Same thing with bar 1. In the future, bar 1 will never be a left limiting bar because bar 3 is smaller than it. So we pop that one off and we say, oh, well, nothing left. So bar 3 has no left limit. Let's just say like the end, nothingness is its left limit. Finally, we mark this one as a possible left limit in the future and we go on to this next bar. Oh, keep the 1, 2, and 3 there. And we go, okay, well, bar 3 could be the left limit of bar 4. In fact, it is because it's the closest available possible future left limit. So we mark it as being the left limit. Okay, same thing as before. We mark bar 4 as a possible future left limit and look at bar 5. For the same reasons before, we want to pop off bar 4 because that's not the left limit here and will never be in the future. Now look at bar 3. In fact, bar 3 is the only remaining possible left limiting bar, and in fact, it is the left limiting bar, so we mark it as such. Finally, get to here. We see, oh, this one is the left limiting bar. We get to here, we pop these 2, same reasons before, pop, pop. We're left with this. Finally, we get here, we go pop. We pop this one here because this one is not the left limit of this one, and because they're the same height, any hypothetical future bar will always have a left limit of here instead of here. So pop, and nothingness is our left limit. But the important thing here is think about the structure of the set of green things at any point in time. It's a stack. It's always going to be in sorted order because whenever we have a smaller thing, we pop everything bigger. So we maintain sorted order. And the most recent thing on the stack is always going to be the left limit. Like here, for example. Why is that? Because green is a set of possible left limits. The top of the stack, the most recent one, is the closest valid left limit, which means it is the left limit because it's the closest one, which could be a left limit. So it is the left limit. And we always, in our example, we always pop from the top. We went, the top, is that a valid left limit? No. No. Yes. So this forms exactly a stack structure. So as we go left to right, we push ourselves onto the stack. We pop anything on the stack that's off the stack that's bigger than us. Pop, pop. Push ourselves on. Pop anything bigger than us. Nothing. Push ourselves on. Pop anything bigger. Pop, leave. Push. Push. Pop, pop. Push. Pop, pop. And then we would push this one on in the future. So we have a stack structure, and we can use this stack to find the left limiting bar of every bar. So that is what sorted stack does. Let me know if it confuses you, because it is quite confusing. But if no one talks, I'm going to assume you all understand how the sorted stack structure works here. So this is just, again, describing it on lecture slides. So I'm not going to go through it in great detail because we just covered that here. But you have the slide for future reference. For the time complexity, each bar is pushed and popped from the stack once. So same argument as before, even though in one step, like in this step here, we go like 2 pops in one step. On average, we pop one thing per new element because overall, everything is pushed onto the stack once, and therefore everything is popped off the stack once, which means overall, order n work. So sorted stack finds all the left limiting bars in order n time. And here is that process in code. So find left limits, we have the input here. We're going to save the output to this array here. We declare a stack. We process all the bars in sorted order. We go while our stack is not empty, and our current bar, and the top of the stack is bigger than our current bar or equal to. So for example, the top of the stack is bigger than our current bar, pop. The top of the stack is equal to our current bar, pop. But here, the top of the stack is smaller than our current bar, don't pop. So while the stack is not empty and the top of the stack is bigger, pop. Keep doing that. Otherwise, if the stack is not empty, the stack is empty, sorry, we have no left limit. We're using -1 here to record no left limit. Otherwise, the left limit is the top of the stack. We then push ourselves onto the stack, and that's our algorithm. Exactly what I did by hand or by the slides described here. So finally, we're almost done here. How do we use the histogram, the sorted stack to solve our full solution? Well, we found the left limiting bar with our sorted stack. So do that. We find the left limiting bar using the sorted stack. We can find the right limiting bar by doing the exact same thing, but instead of going left to right, we go right to left. But otherwise, the exact same thing. It takes order n time, the sorted stack overall, and order n time to use our left and right limiting bars to find the solution. I'll explain that in code. So overall, the complexity is order n. So here's our code. So very briefly, back to our diagram. What do? For each bar, we find this left limiting bar and this right limiting bar using sorted stack. We then go, okay, right minus left minus 1, I believe, gives us our width. We take our height, we multiply together. So back to our code, we go, final slide here, we go find left limiting bars. We do some reverse tricks here to use our same function to find right limits. That's not too important. Look over it in your own time if you're interested, but I'm just reusing the same function by using some reverse tricks here. This is the actual logic. We go, okay, the length is equal to our right limit minus our left limit minus 1. Area is length times height. Update our maximum. Print out the answer. One final note. Here we use long longs. So in C and C++, an int can go from about -2 to the power of 31 through to +2 to the power of 31 minus 1. ish, something like that, or positive, which means an int, the largest number an int can store is about 2 billion, about 2.1 billion. Otherwise, we get what's known as an integer overflow. Depending on what courses you've taken, you know about that, so I won't explain it again. But a long can store up to about, I think, 8 times 10 to the 18. The maximum possible answer is 10 to the 11. So too small, but good enough. So I have to use long for this problem. Otherwise, we'll get wrong answer. So I use longs here to record the area.